They're having different thermal conductivity, temperature T1, this is T2, length L1, and this is L2. Area of cross section, let it be same. This is a junction. I want temperature of the junction. Okay, all of you, junction means the boundary. Find the temperature of the junction. It is similar to like water. Go for the fluids idea. What amount of, these are the two pipes. Capillary series parallel, can you remember? We are just similar idea now. What amount of water flows in this pipe? Same amount of water should flow in this pipe also. So what amount of heat that will flow through this rod? The same amount of heat will flow through this rod. So in fact, given condition T1 greater than T2. So the heat will flow from higher temperature to lower temperature. So according to this, what amount of heat is flowing in this rod, the same amount of heat it has to flow. Sir, how come? Assume there's a water. What amount of water per second is flowing in this pipe? The same amount of water per second should flow through this pipe because they are connected in series. The idea like this. So therefore now heat current across the first rod is equal to heat current across the second rod. So how you define heat current? Temperature difference by thermal resistance. Okay, further T1 minus T. Okay, this will be T1 R2 minus TR2 is equal to TR1 minus T2R1. Let's see that further simplification, what we get it. Okay, let me solve for T. This will be T1. What is R2? How you write it as length L2 by K2A, L1 by K1A. Okay, that K2A, K1A, that will cancel. So T1, L2, K1, T2, L1, K2 by L1, K2 plus L2, K1. Okay, this is the temperature of the junction. Okay, it's a small idea like this. So what is the basic idea? Same amount of heat current will flow across both the rods. This is very important part. Same heat current will flow across both the rods. So like this, we can calculate the temperature of the junction. So maximum all the numericals know will be using series parallel, similar to current LCT ideas, the Ohm's law. That is what we'll be applying. Okay, let's go for series parallel discussion. Okay, if the two rods are in series, so what do you mean by that? I want to replace this with an equivalent. So there's a rod K1, length L1, K2, length L2. Area of cross section, let it be same. So now, so what is, it is like a, this is made up of iron. It is made up of copper. So we know copper is costlier than iron. So I want to replace this with an equivalent rod, which will be cheaper than this. So let's take steel. Steel will be cheaper than iron again. So what should be the thermal conductivity of that? So in that way, what happen? I'm going to replace the things. The same source, there is a sink, T2, T1. I want to replace with an equivalent rod such that same temperature difference and same amount of heat has to flow. Same thermal power. So what is the length of this? Let it be L1 plus L2. Area of cross section, let it be K. This is what equivalent of those two here. So let T be the temperature. Okay, we'll write like this. So what is this? What is the second diagram? Equivalent of these two. That across the source and sink, I connected two rods. They're costly. This will cost you around 200 rupees. This will cost you around say like a 500 rupees. Total 700. I want to replace these two with a material which will be very cheap, say 50 rupees. I think this is good, no? Such that what happens across same temperature difference, same thermal power it flows. So what is the duty of these two rods? They will see that this much of thermal power will flow. For the same thermal power to flow, so what should be the material I should use? And if this cheaper, good, no? Like this is 200, 500, 700, there's only 50 rupees. How much I'll save? 650 rupees I'll save. I want equivalent material. Okay, therefore I'm going to search like this here. So the temperature, let me take that T. So here we can write it as T1 minus T2 equal to, no problem like this. Okay, T1 minus T2, this will become H into the resistance R. Go back to Ohm's law, potential difference equal to, so what you can write? Current into the resistance. So here, heat current into resistance R. Similarly, looking at this rod, T1 minus T, H into R1, T minus T2, H into R2. So therefore, R is equal to R1 plus R2. So how do you can say they are in series if the same thermal power flows? So rather than thermal power, no, better call heat current. If the heat current across the rods are same, they are said to be in series. What amount of water per second is flowing here? The same amount of water flows per second, then they're said to be in series. No, capillary series, the same idea is what applied here. Okay, let's do one thing. What is R? L1 plus L2 KA L1 K1A R2 L2 K2. So therefore, what is K is equal to K1 K2 L1 plus L2 by K2 L1 plus K1 L2. So what should be the material S? If this material, I'll calculate the value of K, I'll go and check the material. If it's very cheap, I'll replace these two by this one equivalent rod. I can save money. So there's a use of that series parallel. It's having wide applications, just like for us, like they are simple numericals here. Okay, what is this K? Equivalent thermal conductivity. So when two rods are in series, what is the effective resistance? R1 plus R2. Thermal resistance, not electrical resistance there, thermal resistance. Okay, can we write this potential, this temperature difference in terms of this temperature difference? Let me bring, and this will be much easier for you. Temperature difference delta T1, temperature difference delta T2. The overall temperature difference is delta T. Okay, how delta T in terms of this we can express. So delta T1, the same heat current will flow. Delta T1, what we can write it as H into R1. And if I replace these two with an equivalent, so what is H? You can write it as delta T by R. And what is R? R1 plus R2. Delta T is what? The sum of temperature difference across the individual resistors when they're in series. Across each element, you can write it, no? Delta T1 is equal to H into R1. Similarly, delta T2 equal to H into R2. What is H? Delta T by R. What is the equivalent of these two? Delta T R2 by R1 plus R2. Very important at many places, this will help us a lot. So what is use of this? If you know the temperature difference across these two resistors, means like, if you know this total temperature difference, delta T, then can you calculate individual temperature difference across resistors? So use this formula. You can use this particular formula. And again, if you know R1, R2, substitute their value or let it be in terms of thermal resistance. So what is delta T1? Temperature difference across R1. What is the interpretation? Temperature difference across first rod. Delta T2. Temperature difference across second rod. Okay, when they're in series, there's a method. So in series, what will happen? The same heat current flow will flow through across each rod. I'll scroll down.